The following program is brought to you by Caltech.
Good evening. My name is Andrew Lang, and as chair of the Division of Physics, Mathematics, and Astronomy, it is my honor to introduce tonight's speaker, Professor Chris Martin. Before I do that, I'm supposed to mention to you that the next Watson lecture will be on November 11th, and will feature Professor Tapio Schneider, who will talk about where the winds come from on Earth and other planets. Now, for anyone like me, and I suspect many of you, who is passionately curious about the universe, there has never been, and in fact may never be, a more exciting time to be alive. Though Galileo first pointed a telescope at the sky over 400 years ago, it has only been in our lifetimes that mankind has developed the technologies necessary to see most of what the universe has to show us. For our eyes are only sensitive to a very narrow range of wavelengths. There's no more than a factor of 2 from the dimmest red to the deepest violet that our eyes can perceive. Yet the universe is telling us a story at wavelengths that span a factor literally of billions, from long wavelength radio waves to the short wavelength gamma radiation. It's only in recent decades, as we've learned to equip telescopes with digital imaging systems, and, importantly, to put them up in orbit, well above the Earth's atmosphere, that most of what the universe has to show us has been revealed. And with each new glimpse, it has never failed to surprise us. Chris Martin has played a major role in this ongoing revolution, pioneering the exploration of the sky at UV wavelengths, about a factor of 2 or so shorter than the wavelengths that we can see. When I was preparing to introduce Chris, I was reminded that for most of my life, I have been traveling in his wake. You see, Chris is a year older than I am, and try as I might, I can't seem to catch up. Chris earned his undergraduate degree at Oberlin in 1978, and he and I first met as fellow graduate students at Berkeley, where Chris earned his PhD in 1986, and I earned mine just a year later. Some years later, in 1993, when I realized that I wanted to move from Berkeley, where I was on the faculty, to Caltech, the first thing I learned was that they had just hired Chris, and were thus unlikely to hire another astrophysicist. But somehow, they managed to find room for me, and I arrived a year later. And once here, both of us, given the fantastic resources we have up at JPL, right next door, we set about developing the orbital telescopes that each of us dreamed of. Chris had his new mission approved in 1997, and I in 1998. Since then, I've been completely left in the dust. Chris's mission, GALEX, was launched in 2003 and has been returning beautiful data ever since. Mine, called Planck, was finally launched just earlier this year. And it'll be many years before I'm here to give a Watson lecture about that. So it is not only with great pleasure, but with genuine admiration and the grudging realization that I will never catch up with him, that I introduce to you Chris Martin, who will describe to you the excitement of exploring the UV universe. Chris?
Thank you very much, Andrew. That was extremely gracious and not completely deserved. It's a pleasure to be here for the Watson Lecture to talk about GALEX, which has been a labor of love of mine ever since 1989, when I first had the idea of doing a sky survey in the ultraviolet, which had never been done. And it turned out it was very difficult and very challenging, and I'll tell you a few of the stories behind that. but in the end, it has paid off, I think, very well. GALEX was launched in 2003, as Andrew mentioned. It's a partnership of Caltech, JPL, and several other universities and Orbital Science Corporation. Before I tell you about GALEX, I want to place it in the context of what we think we understand about the universe, or at least the universe of normal matter, and then tell you something about GALEX, and then I'll tell you about the three major goals of this mission. The first is to measure star formation history. The second is to try to explain that measurement. And the third is to explore the UV universe, which is a very open-ended goal, but I think it's paid off. And finally, very briefly, to talk about what that implies for the future. So the big picture. The universe, in fact, of normal matter consists of mostly things that we do not understand. So and I'm not going to talk about most of that because we don't understand it. 68% is dark energy, which is causing the universe to accelerate. 28% is dark matter, which is fighting that acceleration. And a mere 4% is normal protons, neutrons, what we call baryons, of which only a fraction of a percent are actual galaxies that we can see with our eyes. And that's mostly what we study. This is what we believe is the timeline for the universe. The Big Bang occurred about 13.5 billion years ago. And then there was a period of inflation, which I won't talk about. The universe cooled, and then ultimately a very smooth universe became lumpy, and those lumps created the first galaxies, and finally the universe as we know it now. The lumps that created the galaxies are imprinted on the cosmic microwave background, which is the scientific area that Andrew is pioneering. And this is an image from those lumps that was produced by the WMAP satellite, but that will soon be superseded by the Planck satellite that Andrew mentioned. These very tiny fluctuations, 1/200 millionth of a Kelvin on the average temperature of the sky, which is about 3 degrees Kelvin, ultimately formed the galaxies we know. And this process is called the growth of structure. And this is a very fast simulation of the entire history of the universe, showing how that uniform, smooth matter ultimately collapsed due to gravity, because the regions that were slightly denser collapsed first and formed clusters of galaxies and the individual galaxies making up those clusters. And you can also see filaments connecting the galaxies, and we call this the cosmic web. And there's matter all through the cosmic web connecting the galaxies, but that we have not yet detected. So within this collapsing structure, we can look at a single galaxy. Here's an image from Hubble. This is a galaxy like our own, so you can imagine we're about here. And a galaxy is a collection of about 100 billion stars that are gravitationally bound together. That's actually a remarkable thing in the universe by itself, because when the universe started, the normal matter was spread out in this incredibly tenuous intergalactic space, 1 atom per cubic meter. And then somehow gravity caused this density to increase into a density of 1 million atoms per cubic meter, and then finally a density of many, 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 many zeros atoms per cubic meter into a star. So there's been this enormous increase in the density of matter due to galaxy formation and star formation in galaxies. But it's a complicated, as it says here, it's complicated. And we try to simulate it using computers. We get pictures like this, which convince us that it is complicated. And in fact, the better the computers get, the more the pictures have more and more detail. There's all sorts of interesting physics going on as the gas is cooling and collapsing and forming galaxies. And that process continues probably throughout the life of a galaxy to continue the fueling of the formation of stars and galaxies, as I'll talk about in a minute. Now, I'm going to talk a little bit about some of the mechanics of astronomers and the way they study the universe. As Andrew mentioned, we have in front of us the ability to look at the universe over many, many decades or orders of magnitude of wavelength. Our eyes are sensitive here at about half of a micron wavelength. And in the UV, we can't see the UV because the atmosphere blocks it, fortunately. But if we could, we would see at about 1,000 to 2,000 to 3,000 angstroms, which is 0.1 to 0.3 microns. And there it is. The wavelength is correlated with energy and temperature of the phenomenon that we're looking at. So more energetic and hotter phenomena have shorter wavelengths and correspondingly higher energies of photons. If you know what a photon is, it's an individual quantum of light. And I'll talk about photons in a minute because we detect individual photons. And there's the UV. Now, another important tool we use is the expansion of the universe. You didn't think of that as a tool, but we're actually exploit it because as the universe expands, all the galaxies in the universe recede from each other, and if they emit light at one wavelength because of their motion away from other galaxies, in particular our own galaxy, that light appears to be Doppler shifted, and it's red shifted due to the recession of galaxies. And we can actually use the redshift to measure the distance of the galaxies, because the farther the galaxy is away, the larger this redshift is. So we can actually perform what is equivalent to geology. Geologists look down into the Earth, and farther down corresponds to earlier times in the history of the Earth. And we can do the same thing by looking back farther and farther away. Here's today, and more distant galaxies start to be redshifted to redder and redder colors. We can measure that redshift using by a spectral decomposition of the light from galaxies and determine how fast they're going away from us and therefore how far away they are, and therefore where in the history of the universe we're actually looking at the light, because the finite travel time of light means that we're actually looking back in time as we look at greater distances. Currently, from ground-based telescopes and the Hubble Space Telescope, we've managed to look as far back as almost 13 billion years, very close to the Big Bang. Okay, now I'm going to talk about GALEX itself. Here it is. It's very human size. You can wrap your arms around it. There's the telescope, and the detector and electronics are back here, and the spacecraft itself, which points and powers the telescope, is here, and solar panels. So it's a small satellite, and it's useful to compare it to another satellite you may know about, the Hubble Space Telescope. It's kind of small, and it costs much less as well, which is the good news. But images from GALEX and Hubble have actually been combined in a number of cases because they provide different information. and different ways of looking at the universe, as I'll show you in a minute. Another claim to fame that I think Hubble does not have is that GALEX has found its way onto a Rose Bowl float, and along with Spitzer and some other JPL, some Mars kind of things. So that was nice to see. But I like to think of GALEX as a small explorer. I like to compare it to the great observatories like Hubble and Spitzer. They produce beautiful data, but you pay for it. Whereas small explorers, which GALEX is, cost a lot less, but we have to be smart about what we build for that small amount of money, so we build the right things that have the highest amount of science per dollar. So let me just explain how the GALEX telescope works. Here's the primary mirror. Some light comes in. You can think of it as a photon, if you like. And hits the primary, hits the secondary. It goes through this selectable window or grism. I won't talk about that, but it's a way of dispersing the spectrum. We usually use the window mode. And then it hits a beam splitter, and the short wavelength or far UV light at 1500 angstroms hits one detector, and simultaneously the near UV light, which is at 2300 angstroms, is transmitted and bounced over to the other detectors. So both detectors are simultaneously observing at all times, so it's very efficient. It also has a very large field of view. This is the moon. If you look up at the sky, it's a field. The moon is half a degree, and GALEX has a 1.2 degree field of view. And if you know anything about astronomy, you know it's hard to capture both of these galaxies in the same field, but we can. And this is another way in which GALEX is efficient, by being a very large field of view. And it's a complement to the Hubble Space Telescope, because the Hubble Space Telescope has a very small field of view, like a soda straw, and it's really designed to study particular known objects that have been found by surveys, such as GALEX. GALEX looks over large parts of the sky, finds both large numbers of objects, so you can make statistical measurements of different questions, and also finds the needles in the haystacks, those rare stages of evolution that tell you something incredibly special about astrophysical objects. Here's the telescope again, half a meter in diameter, or 24 inches. And it's also got a very large secondary, if you know anything about telescopes, because of the very wide field. The detector is unique. It's a photon counting detector. So a photon comes in. There's a photon, goes through the window. It creates something called a photoelectron, which one for every photon. And then that is amplified by this thing, which is basically a bunch of glass tubes which has high voltage on it. And it produces about 10 million electrons for every one of these. And then those 10 million electrons fall on a position encoding device, which uses the time of arrival of the signal. So you get a pulse on that direction, you get a pulse in that direction, and the difference in time tells you where you are in this direction. And then there's another encoding anode in the other direction. So you get a two-dimensional position for every photon that arrives. So we actually constantly are moving the satellite at all times, and if we didn't correct for this constant motion of the satellite, this is what an image would look like if you just added up the photons as they came into the detector. But we actually correct that all the time with processing on the ground, and we get images that look more like that. Okay. Another interesting thing about GALEX is that it flew on a Pegasus. A Pegasus is a winged rocket, and there's a picture of it. And I'll show you the launch, or I'll show you a launch. Here's the satellite folded up and mated to the launch vehicle. And it took off in the morning of April 28th. But before I show you the picture of how this works, I mentioned that we had a few problems. And I don't want to really talk about them because they make me upset, but you can read them. And if you can't read fast, you can just read the red words, because they give you the sense of what happened. We kind of got the idea that maybe we had bad luck. So after a while, if something like this would happen, people will just say, "Oh, it's GALEX," you know. But in the end, it all worked beautifully because we had a great team developing it, and people at Caltech and JPL in particular, Berkeley and Orbital. Here's a picture of some of them, and amazing team, and I'll mention some names at the end.
3, 2,
so,
1, drop.
One of the things that didn't work, you can see the launch worked, but this is not our launch. But what happens is the L-1011 flies out over the Atlantic and drops the rocket. It flies aerodynamically after its launch for a short period of time, and then it separates and becomes a rocket. It's a very cheap way to get a small satellite into orbit. So there have been a number of successful launches from Pegasus. Okay, and now I'm going to turn to a discussion of the science. And the science team has also been outstanding. Here's the science team at one of our meetings. And we have members of the science team from all over the world, in particular France, Columbia University, Berkeley, Germany, and Johns Hopkins, as well as Caltech. Okay, so I mentioned the 3 GALEX goals. The first one is star formation history. Now, what do I mean by that? In order to understand how galaxies formed and evolved with time, the number one thing we really need to understand is how galaxies were built up. And what I mean by built up is the gas in galaxies is converted into stars. That's how a galaxy is built. A galaxy is a collection of stars. So the star formation history is the history of that for each individual galaxy and then for the collection of all galaxies. Okay, you can imagine the Big Bang. In this plot, the Big Bang is on the left and today is to the right. So time goes left to right. You can imagine a star formation history that is constant. An early peaker. Midlife crisis. Late bloomer, or an erratic. And galaxies exist that have all these different star formation histories, it turns out. But how do we measure this? And this brings us to the question of why we look in the ultraviolet. So some of you may be familiar with what is basically the Rosetta Stone for studying stellar evolution, and that is the Hertzsprung-Russell diagram. And what you do is you basically take a star and you plot its temperature on the horizontal axis and its brightness on the vertical axis. And what was found when this was first done, and you have to measure the brightness by knowing the distance and so on, is that most stars lie on a line, which we call the main sequence. And it turns out that they lie on this line because they go through the majority of their life burning hydrogen, which is their major source of fuel. And so most stars are actually in that process because it's the longest part of their lives. Then at some point they evolve, they run out of hydrogen, they start burning heavier elements, and they evolve to other places on what I'm going to call the HR diagram, just for shortness, and they become different kinds of stars. And that's been a tool, this diagram has been a tool for studying stars for a very long time, much of this century, this past century. Now I'm going to simplify it by just plotting the stars on the main sequence. And here's the brightness, the temperature, and remember that the hotter temperature stars radiate in the ultraviolet, and cooler stars radiate only in the visible, and even the coolest stars radiate only in the infrared. And it turns out that the brightness is directly correlated with the mass of the stars. So the most luminous, hottest stars are also the highest mass stars. And it turns out that because, even though they are the highest mass stars, they're so much more luminous than their fuel content, if you look at the numbers over here, that they run out of fuel really quickly. So they have very short lifetimes. They burn bright and hot, but they live fast and die. So there's the main sequence. And the sun, by the way, is about here. It's about 5,000 degrees, and it's one sun worth of brightness. Okay, galaxies evolve off the main sequence for various reasons, but high mass stars blow up because their core actually collapses, and that causes a supernova explosion, which expels the envelope of the star out into the interstellar medium, and that envelope includes all the chemical elements that were produced by the fusion process of burning the hydrogen in the stars. And those heavy elements pollute the interstellar medium, which early in the history of the universe contained mostly hydrogen and helium. So the reason that we are here with our carbon and nitrogen and oxygen and all the other heavy elements is ultimately because supernova explosions, massive stars formed the heavy elements, and then they exploded and expelled them into the gas that forms the next generation of stars and planets, and ultimately life. Lower mass stars, the sun, or a few times the mass of the sun, turn into red giants after they live. They may live 100 million years if they're 5 times the mass of the sun. And they turn into red giants, something called an AGB star. And I'll mention that now because I'm going to show you one at the end, which is quite interesting. And then ultimately something called a white dwarf, which is like a brick, basically, a star that looks like a brick. Before they do that, they also expel their envelope, and they produce something called a planetary nebula. And this is a GALEX image of one of those. By the way, all the GALEX images I show you are ultraviolet, but of course you can't see ultraviolet. So we've made them longer wavelength by making the far ultraviolet blue and the near ultraviolet yellow and combining them in a picture in which the blue is bluer and the yellow is yellower, but it's all in the ultraviolet. Okay. So because of the evolution of the massive stars, imagine we form a bunch of stars of all different masses, all at the same time. So they're all cohorts. What happens as the clock runs? Oh, there's the main sequence again. Sorry about that. So they're born. After 10 million years, notice that the most massive stars are gone. They've exploded into supernova explosions. After 100 million years, the next most massive stars are gone. They've turned into white dwarfs. And as the clock continues, we lose more and more stars at the massive end of the distribution until we get to the point at about 10 billion years where stars like our sun will die. They will turn into red giants and then white dwarfs. So what does that mean? Well, the UV stars die after 100 million years, which is a snap of the fingers on the cosmic clock. 100 million years sounds like a long time, but galaxies are pretty slow. They don't change that rapidly. And that turns out to be a short period of time. And if stars form, then they produce UV, and if the star formation stops, the UV stops. So when you see UV, that tells you that star formation is going on now, or it's been going on for 100 million years, which is basically in the last instant of time. So here's a picture of a well-known galaxy, the Andromeda Galaxy, in the optical, where we see lots of stars in the middle. And those are old stars. They're the stars that haven't died yet, but they're the low-mass stars. They were formed almost 10 billion years ago, whereas there's a little bit of gas and star formation going on in the outskirts of the galaxy. You can kind of see that the stars look a little bluer out there, but it's not so obvious. But when you look in the UV, the picture completely changes. Basically, all the light except for the very center goes away, and you see all the light in this ring of star formation around the outskirts. So even though this is not a galaxy that's forming stars very actively, because the UV only shows you the recent star formation, even if there are old stars around from the early history of the galaxy, it picks out the recent star formation on top of that old stars and tells you exactly what is going on that is building the galaxy now. So it's telling you about the current building history of the galaxy. An analogy would be, let's say you wanted to understand how a house was built. Okay. If you take a picture in the visible, you get stars that are 1 billion years old, 5 billion years old, 7 billion years old. Everything changed during that period. The galaxy completely built itself. So you get a very long exposure picture of a house being built, okay, a galaxy being built. Whereas in the UV, you get to watch it being built, just like that. This is real time. No. There are no contractors that fast. And you can actually figure out how the galaxy is built by watching it being built. Now, there's a subtlety here, and that is one we face in many fields of science, and that is you can never watch a galaxy evolve because we don't have 5 billion years to sit around and wait. The funding doesn't last that long. So we have to study evolution by trying to find galaxies that are like each other at different points in time and make a connection, connect the dots between those two galaxies. And to do that, we actually need a lot of galaxies because galaxies are different in many different ways. So we have to find so many galaxies that we can find the two that are similar, except the one thing that changed was time. Okay. So here is, now I'm sorry, I reversed the time axis here. The Big Bang is now on the right, and we are here today on the left. This is the way, so time is going from right to left. And this is what we believe, based on some measurements, the cosmic star formation history is. We add up the star formation from all galaxies. We want to measure, using the ultraviolet, the average star formation rate in the universe by taking basically the ultraviolet brightness of the galaxies and adding it all up. And that tells us the total rate at which stars are being formed in all galaxies. We want to do that today, and then we want to look back in time by using redshift as far as we can from the space ultraviolet, and then from the optical, we can look even farther back. With GALEX, we can look back to around here. We want to use the same technique, so we want to use the same ultraviolet, just redshifted, to give us different times in the cosmic history. So the way we do that is we perform 3 surveys. We perform an all-sky survey, or a most-of-the-sky survey. And we look everywhere, but we look shallow. We don't look far, and we get a big piece of the sky, but not very deep. So if you add up the total volume in that, you get 1 billion cubic parsecs, which is about 27 billion cubic light years. Okay, so it's a pretty big volume. We get this with 100 seconds on any given target, and this is what you see in a field that's about 10 by 10 arc minutes. You see maybe a few dozen galaxies. Okay, and here is one piece, about 1% of the All-Sky Survey, showing our own galaxy, some of the interstellar medium from our own galaxy showing up in various ways in this very interesting image. There's lots of things here. We actually have to avoid certain regions because they're bright stars. We can't look at really bright stars because we count every single photon, and the detector gets upset. Okay, the next survey. So we want to go farther back. We do what's called a medium survey. We go back to this point with that, and we look at a smaller piece of the sky, but we go deeper, and you can see here what we see is now we're seeing maybe a couple of hundred galaxies. And again, we're looking at a volume which is about the same, about 27 cubic billion light years. And we're looking back now in time about to 9 billion years after the Big Bang. Finally, to go the farthest back, so we're up to the top of this peak in the star formation history of the universe, we do a deep survey. And for that, we look at a smaller region of the sky, but we look very, very deep. And now this image has maybe 1,000 galaxies in this one tiny piece. Again, we go back to about 5 billion years after the Big Bang. We're looking again at about 27 billion cubic parsecs. And we get a lot of galaxies. This is our deepest image of the Deep Imaging Survey. And it's about 100,000 seconds. There are 30,000 galaxies in this image, which I think is amazing, just in one picture. So what have we learned? Well, we have made this measurement and found that indeed the star formation rate in the universe went up by a factor of 10, going back from today to looking back about 7 billion years ago, or 5 or 6 billion years after the Big Bang. And not only that, we can say something more subtle, which is that the biggest, most massive galaxies had a very large star formation rate early in the history of the universe, but they've died off. And we'll talk about that in a minute. Whereas the less massive, fainter galaxies are actually doing just fine now. In fact, they may even be going up. So there's something very different about the star formation history of big galaxies and smaller galaxies. Now, in order to say more and try to understand this star formation history of the universe, we need a tool like the HR diagram for stars. So here's the stellar HR diagram. Now I'm going to turn it around so that now brightness or mass goes this way and temperature goes up. We're going to talk about a new thing, which is a galaxy Hertzsprung-Russell diagram. Is that possible? We'll see. So in this picture, these are blue or hotter galaxies. These are red or cooler galaxies. These are more massive galaxies. And what is the temperature or the color really telling you? Well, it's telling you blue stars or hot stars are formed from recent star formation. So it's telling you the star formation is high. And we divide that by the stellar mass because we want a per capita, because galaxies come in all sorts of masses, from really tiny to huge. So we want a per capita a measurement of how fast a galaxy is forming stars, compared to how many stars have already formed over its entire lifetime. So this is this ratio, the star formation rate divided by the stellar mass in a galaxy, basically is the color. So a blue galaxy has more star formation, a red galaxy has less. But when you do this in the optical, it turns out the picture is very is difficult to discern, but when you do it in the ultraviolet, as I'll show you, you get a much clearer picture of how this works. Now, another way of looking at galaxy types is, the Hubble classification of galaxies, the tuning fork, and to make it equal to the previous plot and all the future plots, I'm going to plot it, put it on its end, so that spiral galaxies are at the top, and these are the galaxies that are forming stars, and elliptical galaxies are at the bottom, and these are the red galaxies that are no longer forming stars. And one of the questions that we've been trying to answer for decades in astronomy is, what causes a galaxy to be a certain type? Spiral, elliptical, blue, red. And it boils down to this, the old question of nature versus nurture. Okay? Do galaxies get formed with a certain set of characteristics and stay that way throughout time? Or are they affected by their environment, other things that happen around them, and so on? We now, and two ways of looking at that, here's a galaxy. The nature or the DNA of a galaxy, where would that be? Well, it could be all galaxies sit inside something called a dark matter halo. That dark matter I mentioned at the beginning of the talk has collapsed, and in fact galaxies form at the centers of these collapsed halos of dark matter. We still don't know what the dark matter is, but we know that the galaxies are sitting in the center of these lumps of dark matter. And it could be that something about that, like it's spinning or it's flat, it's a funny shape, could determine the galaxy's fundamental properties throughout time. But another possibility is that where a galaxy lives and who it interacts with, other galaxies, determines its evolution over time. So here's galaxies in clusters, nice Hubble Space Telescope image. Okay, so galaxies, well, one of the things we have found with GALEX is that when you plot the galaxies on this galaxy HR diagram, that the blue galaxies appear to form a sequence. They appear to be tightly arrayed on a line, so that means their properties are very similar. There's a small dependence on the mass of the galaxy, but otherwise they more or less have the same color. And you can see that when we look at all the blue galaxies, it's kind of amazing, these pictures from GALEX. They all look different, but they're all the same color. I'll just show you a few. They all have interesting structure, which is telling us something about the star formation processes in these galaxies. Now, there's another group of galaxies on the HR diagram, which are kind of like the stars that have evolved to the red giant phase. These are galaxies that have stopped forming stars, and they're what we say are passively evolving because they're no longer forming stars, so we're just watching what happens when the individual stars in the galaxies get older and older. The more massive stars die out, the cooler stars stick around for longer, so the galaxy gets redder and redder. So this is what we see. When we look at them with GALEX, well, they're pretty boring. They're just little fuzzballs of stars. There's not much going on because, of course, they're not forming stars. So we shouldn't even see them, right, because we're looking at GALEX. In fact, we only see them in the near UV channel, the red channel of our two channels. We don't see them in the other channel. They're so dim. So that's interesting. Now, we now believe that if we were to watch a galaxy evolve on this HR diagram, that we would see something amazing. Whoops. If I clicked it, we would see something amazing. So here's the path of the galaxy on the HR diagram, and here's what we might see. This is, we don't know this for sure, but the galaxy is transforming itself as it moves to different parts of the HR diagram, from a blue galaxy to a red galaxy, and it goes through this phase of being green, which is a good thing, and it moves around a lot, and it does all sorts of interesting stuff, but the galaxy is not constant. It's changing its shape, its morphology, its color, all at once. So galaxies are evolving with time. And if we understood how galaxies evolve in that sense, we would understand much more about how galaxies are built. So what is really interesting are these galaxies that are in between, the ones that are forming stars very vigorously and the ones that are basically not doing anything at all, these green galaxies, which we believe are transitional from the young star-forming galaxies to the old not star-forming galaxies. And here's a few examples of green galaxies. And they have some evidence of star formation, and they have some evidence of elliptical galaxy kind of morphology. They look like they're in a transitional state. A couple of examples. Here's a galaxy. Here's the optical picture. It's just a little fuzz ball. Doesn't look very interesting. When we looked at it with GALEX, this is what we saw. This fuzzball is got a tail of blobs coming off the back of it. And it turns out that this galaxy is in a cluster, and the cluster has hot gas in it. The galaxy is moving through the cluster. That gas is pushing the gas in the galaxy out. And if it doesn't have gas, it starves. It stops forming stars. But in the process of pushing the gas out, it actually started new stars being formed. And so this galaxy is in the process of being evolved by its environment. Here's a very bright star. This actually illustrates two things. Here's the galaxy that's interesting, NGC 5050. This is what you see in the optical. When you look in the ultraviolet, first of all, the bright star goes away because it's red. And then you see around this red galaxy evidence of new star formation in a ring. So the galaxy maybe is being reborn. It started to die, and it's being reborn by new star formation. So this process of complicated evolution could be studied in the visible band, and what you would see is something like this, where, again, this is basically the color, the ratio of the blue to the red luminosity or brightness. This is 1.1, and this is the brightness in the visible. And basically, it's all kind of squished together. If you don't even know what's going on, what these little dots are individual galaxies evolving on the HR diagram, just like a star would. But you can't see anything because there's very little difference between the two colors in the optical, the blue and the red. But if you compare the UV to the red, the optical, it magnifies this diagram so that you can see what's going on. Now the galaxies, individual galaxies, are evolving on the diagram. This is maybe 200 of them all at once, evolving from the Big Bang all the way down to now. And you can see they're changing their properties all the time. It's an enormously dynamic, complicated problem because, and this is a model, this is not what we've measured yet, but the models say that galaxies are constantly being changed from one type to another by getting new gas that forms new stars, interacting with other galaxies, merging. So they're very dynamic. What it also says is that galaxies, one of the reasons why the star formation rate in the universe was high in the past and is much lower now is that many galaxies have lost the ability to make stars, but we don't know why. So the next goal of GALEX is to try to explain that star formation history. This is one theory. Gas goes into a machine, and out comes stars. And it's actually not that far from the truth. Whenever there is gas, we get stars. And that's one of the things we've discovered with GALEX. So the first step in the process of forming stars in this machine is that gas has to come from somewhere. And we believe it flows in from the intergalactic medium, the cosmic web that surrounds and threads all the galaxies in the universe. So gas flows in. We do not understand this process. Okay, let's leave that on the table. We have some evidence from GALEX that this is happening. Here is a galaxy where this is an infrared image, so this just shows the stars that were formed early in its life. In the center, lots of star formation, but nothing outside. In the visible band, it's a little bit bigger. You can see some evidence for star formation. When we look in the ultraviolet, we see a completely different picture. All around the galaxy are these regions of star formation, far outside the main part of the galaxy. And one of the explanations for this is that new gas is flowing in from the cosmic web to fuel ongoing star formation in the outer parts, the exurbs of the galaxy. Here's an example of a known ring of gas that may be primordial. It's seen in the radio band. It's just hydrogen, as far as we can tell. And GALEX discovered that there are, within these contours show where the gas is. Within these, if you look very carefully, are blobs of new star formation. This is a gigantic ring, hundreds of thousands of light years in diameter. And yet, it was never known until GALEX flew that within this probably primordial ring of gas are new galaxies being formed today. So there's gas, there's star formation. How does that work? Well, gas has to be compressed by some process. Once the gas gets to a certain density, then gravity takes over and stars form. How does compression, the initial compression, occur? Well, we know that spiral waves in galaxies are a way of producing this compression. Here's one example. Here's another showing star formation occurring on the spiral arms. And the one way of understanding this is these are individual particles, and you get this buildup. It's kind of like a traffic jam along the arms, which increases the density. And some galaxies show this phenomenon, and some do not. That was obviously a YouTube video. Amazingly, there's an analogy which you may have experienced from the Mathematical Society of Traffic Flow. It happens in traffic. And, an instability occurs. Someone is texting or on their cell phone. They slow down a little bit. They create a disturbance which actually lasts much longer than the original car. It propagates like a wave through the traffic. And you go through it and you say, what is going on here? You don't know, because it could have occurred minutes ago or even. So that's a phenomenon very similar to spiral waves. But many galaxies don't look like that. Some, we call them flocculent. A poetic name. They look kind of blotchy. And some people believe that the compression here occurs from turbulence, like the turbulence that you see when you look at clouds, that it's turbulence due to the shearing winds in the atmosphere. They look very similar. Turbulence could be generated by gravity or by the stars blowing up, the supernovae in the galaxy itself. That's another possibility. Another way to generate collisions generate compression of gas is collisions. Here's the Cartwheel galaxy, a beautiful ring-like structure, and there are a number of these that we see in the sky. And this is an image involving GALEX, Hubble, Spitzer, and Chandra all together, a beautiful image which has been displayed all over the world, I can say. We have and the star formation from the GALEX, which is in the blue, is clearly happening in this ring. So this is a case where a collision occurred and created like a boulder dropping into a pond, a perfectly circular wave coming out and producing star formation. And here's a simulation of that, sorry. So a galaxy collided with the main galaxy and, like that stone in the pond, and produced a ring propagating outward. Okay. One more case of colliding galaxies. This is the antenna galaxy. Two galaxies collide, and due to the collision, gas is pulled out of the galaxy. And the gas, as it gets pulled out, also gets compressed. And you actually see that this is a blue, what we think is a new galaxy at the end of this tidal tail, which we can actually age date it using its color and tell you that it's younger than this interaction. So it must have formed due to the interaction. And there it is. There's gas there. There has to be gas. The contours show where the gas is. There has to be gas to form the stars. And here's a simulation of that. The formation of a new galaxy by an interaction. So these giant tails get created, and the gas in them is compressed and forms new stars, and potentially new galaxies in the process. So the story goes on. There's one more way to compress gas, and that is if you have a massive black hole in the center of a galaxy, it can produce relativistic jets that come out. And here's a case, this is called Centaurus A, where if you look way outside the galaxy, again, about 100,000 light years outside of the galaxy, you see new stars being formed by the jet hitting gas that happens to be sitting out here. The collision causes the gas to compress and form new stars. And with GALEX, we pointed at it for half an hour and we saw it instantly. Okay. The final piece of this story is that once the gas collapses, it forms clouds. The clouds collapse into smaller clouds, and those individual clouds form stars. And because the dust in the cloud absorbs UV or scatters it, just like the smog does, absorbs and scatters light, the UV view of this process looks like that. We don't see anything. That's why we have other observatories looking at other wavelengths, like Spitzer, which looks in the infrared and gets these beautiful pictures of what happens inside the star-forming clouds. But in the end, the UV wins because the dust, well, first of all, the dust is heated by the UV, so that produces infrared. So the hot dust gives us infrared radiation. But the UV, the energy, and also the exploding stars, the most massive stars that explode, end up disrupting, there's the hot dust emitting the infrared, and this shows that this is a Spitzer picture in the infrared showing the hot dust, and that's wherever there's dust, there's gas, and wherever there's gas, there's star formation. So the two maps look very similar on the global scale. So that's because the warm dust is being warmed by the UV. Then the stars, as I was saying, explode and disrupt the dust, so now the UV can get out. And we can see an example of that in this picture of Andromeda, where this is the side-by-side Spitzer infrared and GALEX UV view. If we look at this one region and blow it up, there's a star cluster, which we see in the UV, but if we look at the gas, there's a hole, and if we look at the dust, there's a hole. The stars have made a hole in the gas and the dust by disrupting it. And here's a galaxy where the effect of that feedback of the energy from the stars actually causes the whole galaxy to appear to explode. M82, here's the GALEX picture, is shooting matter out into the intergalactic medium, dust, gas, heavy elements like carbon, nitrogen, and oxygen that are actually seeding the intergalactic medium with these new elements. Okay. So there's much more to say about that, but I want to talk about one special kind of galaxy, and that is the galaxies we see in the distance. The galaxies that are forming that peak in the star formation history, galaxies used to be different than they are now. And when we look with Hubble Space Telescope, we see them, and they look very different because most of them are early in their lives. They're young galaxies, and their light has been redshifted. We would like to find in a local universe galaxies that look like these distant galaxies so we could study them in detail. And here's a picture showing how the light from distant galaxies, which is in the UV, actually appears in the visible when we look in these deep Hubble pictures. So we actually are looking at the UV of those distant galaxies. So we would like to see galaxies that look the same as these distant galaxies to understand them. But very few galaxies look like those. The distant galaxies look like these lumpy things, and the nearby galaxies look like this galaxy, very smooth, and the star formation is occurring very smoothly as well, and very slowly. But we have found, with these very large surveys, surveying as many as 300 million new galaxies with GALEX, a very small number of galaxies which look very similar to these distant galaxies. There's about one of these, what are probably analogs to primordial galaxies, in every one of these images I showed you, one per degree of the sky. So they're very few. You have to look in many areas of the sky to see them all. But we've found now as many as thousands of them with the GALEX surveys. Finally, I want to talk about a couple of the discoveries we've made that fall under the goal of exploring the UV universe. That's not really a goal because it doesn't have real objectives. Discover something. Okay, go out and discover something. Well, you always want to do that, and whenever you look at a new part of the spectrum, you're bound to discover something new. You can't write that in a proposal, but you know it's going to happen and you want it to happen. It's the best part of the business. There it is, the question mark. Here's an example. We call this the Blue Ring Nebula. It's really faint. It's 100 times fainter than the night sky on the ground. And we saw it immediately. But we still don't understand what it is. No one knows what it is. We have not figured out what this thing is. It's a normal star with a nebula around it. Okay? Another thing we found. This just shows you a galaxy which got brighter. The dark means it's brighter. And then it got dimmer again. So it had a flare. A whole galaxy had a flare. That seems unusual. Well, it turns out that what happened is that in the galaxy, there's a black hole, and that black hole swallowed a star. It actually tore the star up, and the star got spread out and radiated in the ultraviolet for a while, and that produces this ultraviolet flare. And we've discovered several of those as well. And if you didn't see those, you wouldn't know that there was a black hole at the center of these galaxies. In our own galaxy, here's an example of one of those asymptotic branch stars, AGB stars, a star that's evolved off the main sequence. It turns out that it emits a lot of dust and gas as it's dying. And here's a star where we've seen the gas being emitted, and it's being blown back by its motion through the interstellar medium, and we think it's producing a new cloud in the gas between the stars, the interstellar medium. So this is the first time we think we've seen a star producing a new cloud that will ultimately go on and produce new stars. But there's an even better example of that, and that's the star called Mira, which everyone knows. Actually, this star has been known for more than 400 years. It was discovered by David Fabricius, an amateur astronomer, professional theologian. He discovered a star that changed its brightness by a factor of more than 100. It sometimes was visible to the eye, sometimes was not, in about a 300-day period. So for 400 years, this star had been observed by all the telescopes on the ground and in space, and it was considered an isolated star. And then GALEX looked at it and found this. So the star is emitting this wind of gas and dust. It's moving through the galaxy very fast, and the gas in the galaxy is blowing back that wind and star into a tail. In fact, it's a very long tail, 13 light years long. It's 2 degrees on the sky. It's one of the largest astronomical objects ever found on the sky, and it had never been seen until GALEX flew. I think that's amazing. And here's what it would look like if we had a really big telescope and looked back in time. The star is evolving its wind, and then it's moving through the interstellar medium, and like a smoke trail being dragged back by its interaction. Okay. What about the future? Well, we've tried to explain, we've measured star formation history and found that the galaxies have stopped forming stars as fast as they used to in the past, a factor of 10 lower. We've discovered basically that anywhere there's gas, there's star formation. So it must be the case that the star formation history has to be explained by understanding how the galaxies get their gas, what gives them their mojo forming stars. And the future of my group's efforts is to try to actually measure this gas between the galaxies. This is a map of what the galaxies look like in a very large cube of the universe, the baryons, or the bright baryons. And if we could measure the dim baryons, the intergalactic medium, we would get a picture like this. So our next satellite, which we're working on, hope to fly in the next decade maybe, will be trying to actually make a map of the gas that spans between the galaxies, the cosmic web, which feeds and nurtures and fuels the history of star formation throughout time. So with that, I will thank you and mention just a few of the people, again, who played a key role in GALEX. The project manager, Jim Fanson, many people from JPL, Patrick Morrissey, the detector scientist, and a variety of other people at Caltech, NASA, and my family and my Steinway. Thank you.
This program is brought to you by Caltech. Visit us at caltech.edu.